Okay, so last time we were in the middle of this lemma, this upper bound lemma. So this is to do with the multilinear constant depth circuits or formulas. So what it is saying is, if you randomly partition your variable set into equal parts y and z, then the measure is with high probability, where the probability is this. So with probability, so if the circuit size s is smaller than this exponential, then essentially with constant probability very close to 1, the measure will be smaller than 2 raised to n by 2. So 2 raised to n by 2 is the max possible measure, and there will be a reduction by this factor of 2 raised to n raised to something. Okay, so that's the upper bound, and which would mean that if you take a polynomial f whose measure is large, then you will get a lower bound on s. So the way we would do this is multilinear T product decomposition. Right, so we will write f as essentially a sum of multilinear T products, plus there is a G0 term, which is the kind of term to ignore. So these are the low degree monomials, which does not contribute much to the measure. So then the question reduces to studying GI, gamma GI. Right, so that is what we were doing. So we are looking at this G, that is product of H1 to HT. Each HI depends on at least T. So the variable set of HI is Xi, and that we are assuming is at least T. And we pick Y, which is a subset of n by 2 variables of X randomly, and then we will study what goes in Y and what goes in Z for the Xi variable set, right. So this imbalance will be called Di, and we will say that Xi is K imbalanced if this imbalance or discrepancy is more than K, is at least K. Bi we have defined to be essentially the size of Xi. There is a factor of half. So this calculation showed this simple upper bound, that the measure on G is the max measure divided by a product of 2 raised to discrepancies. So basically sum of the discrepancy is or sum of the imbalance is what you get as negative in the exponent with n by 2. So we will now show that one of the discrepancies is large, which will mean that gamma G is small, which will mean that gamma of multilinear depth delta circuit is small. So for that the analysis is through hypergeometric distribution, right. So what happens when you pick a random subset R, so how many elements of a fixed set A will be picked? So the k of them will be picked with probability 1 over square root A. A is the size of big A. So we did this simple calculation, and yeah, so now after that detour we will analyze the probability of all these events happening simultaneously, which is all the discrepancies being smaller than k, right? That's the event. So the first probability is that d1 is smaller than k, then second is assuming d1 smaller than k, d2 is also smaller than k, and so on. So we will now study this expression, this conditional probability. So probability of E1, right? What is that? That is the base case. So probability of E1 is, it is basically the probability over this random choice of y, n by 2 subset of 1 to n, and discrepancy less than k means that x1 elements that you pick in y are between b1 minus k and b1 plus k. Right. So these are the essentially 2k values that you are allowing to y intersection x1, and so from hypergeometric distribution you will get this to be less than equal to k times order of 1 over square root of, what is the size of the fixed subset? x1 size is 2b1, right? So you will get this. Is that clear? That lemma had some assumptions. You just have to check that those assumptions hold. So there was this assumption that when you are looking at the cardinality to be k, the subset should be bigger than k, and subset itself should not be much bigger than 2n by, should be at most 2n by 3. So those assumptions hold in our case. So we are assuming subset which is 2b1 is less than equal to, so 2b1 is the size of x1 which is less than equal, which is equal to n by 2, and so that is clearly less than equal to 2n by 3, and that is at least so what is b1 minus k? What is k in this case? K, so this is the discrepancy bound. We'll pick it to be very small. So we'll make sure that it's we'll pick it to be less than equal to b1 by 2. b1 by 2 means n by 4. Okay, we'll pick k to be quite small. So this the moderate assumptions will all be satisfied. So for every value between b1 minus k and b1 plus k, you can apply the hypergeometric probability calculation. Okay, so this is not very important. Those assumptions were anyways quite weak. So assuming all that, you have this bound for probability of E1, that is d1 less than k. So let us now move to the general case, which is consider EI given the previous events 1 to I minus 1. So since x1 to xi minus 1 are partitioned in a balanced way, right, because when you assume that E1 to EI minus 1 events have happened, then basically what you get is for all j less than equal to I minus 1, dj is less than k. So discrepancy is less. right? So we read it as they being partitioned in a balanced way. So we deduce that so we'll calculate this now. So basically, things that remain. So x1 union dot dot xi minus 1. Well, they are disjoint because we are looking at this T product, right? So these variable sets, subsets are disjoint, and so what remains, we want to see its intersection with y. So this will be y intersection x minus y intersection with the union. So what is y intersection x? That's n by 2. Sorry, not, you won't be able to get an equality, but what can you say about this? Well, first of all, this expression y intersection, this union complement, do you want it to be large or small? So remember what you wanted to study, EI, right? So you want this to be small. So you want an upper bound here. And if you look at this y intersection x1 and x2 and xi minus 1, you have a lower bound for this, because for these the partition happened in a balanced way. So you actually have both lower and upper bounds. So what is the lower bound? So this will be less than, put each of these lower bounds. So y intersection x1 is at least b1 minus k, and with x2 it's at least b2 minus k, and bi minus 1 minus k, which is n by 2 minus b1 minus I minus 1 times k. What is this term? It should be plus, sorry, plus. Right, so this is essentially the size of x prime, which I am defining as, let's write this properly. Complement. So the prior variable subsets, their union, so what remains, that is x prime. So what this inequality is saying is that y will not pick, it's not x prime, sorry, this should be, oh, b1 we had defined itself as half, it's x prime by 2.
It is x prime by 2.
Yeah, that is where there was some semantic issue. Yeah, so now it's fine. So this is x prime by 2. So what this is saying is that y will use from x prime around x prime by 2 many elements. So the partition with respect to x prime will be ik balanced.
Because k.
Yes. No, sure, all these things will make sense only when k is small. Yeah, otherwise you don't get anything. So the way we will read this is that partition of x prime by y z parts is IK balanced. Yeah, so even when you are looking at this intermediate probability or probability of the intermediate event, the partition is nearly balanced. Okay, so the situation is not very far from even. Even at the ith stage, the probability calculations will be very similar to the probability calculation for E1 event. So this will drastically simplify our calculations. So we'll just behave like, we'll just do what we did with E1. We'll get the same expression. So assuming this IK to be much smaller than n, we redo the calculation. Like E1 and still get that the probability of EI, assuming that prior events have happened, so this is the same as we got here, right? So which will be k times big O of 1 over square root of what? Bi. Is this part clear? So I mean, this can only be understood by so quickly by the extreme case. The extreme case is the partition is perfectly balanced for all E1 to I minus 1. So if the partition perfectly balances them, then at EI also for the remaining variables it is perfectly balanced. So you get the same probability estimate as you got for E1. And what was I?
Okay, so initially that K balance was 1 K balance. That is, so it's IK balance, right? Initially we take
Yeah. So we could put here IK, but yeah, we could put here IK, but I think I is also very small in the end, so it will not matter. Yeah, because I is upper bounded by T, and we'll pick T to be very small. Yeah, it will not matter in the end. So you will soon see. So once we have this, we can now get the probability of intersection. So probability of the intersection of all these events is then, just take the product. So that's k raised to t and correct. So all these xi being balanced, that so for that this is the probability, which means that, which implies that the estimate that we had gotten for gamma, right, that is large. So let's write that in those terms. So this means that probability over y, that gamma yz of g is bigger than this. So this is because this 2 raised to minus k, this is coming from the sum of the discrepancies you had in the denominator or in the exponent which was in the denominator. So you're assuming all of them to be quite small, right? That has to happen for this measure to be large. So this is certainly upper bounded by the probability we just calculated. Right, so we have now the probability estimate for the measure being large. So all that remains is you fix the parameters and show that this is a very low probability as long as the size is small. So in particular, on fixing this k to be t raised to 1/3, we get the probability right. So what will you get? In the numerator you will get so you basically get product of t raised to 1/3 in the numerator, and in the denominator what are you getting? What is square root of bi? Right, so how is that related to t? At some point we had
K and G are equal to product of V1 to V2.
no, we had some assumption. We had this. It's at least t by 2. And t also, remember we had something in the no, but did we fix t in the proof? Yeah, we have not fixed it, but it will be fixed to this lemma statement, basically whatever expression you are seeing in the lemma statement. Yeah, so let's come back to this. So this is square root t and I is going from 1 to t, right? So you get this. So what is this? This is 1/3 minus half, right? So that's 1/6. So t raised to minus t by 6. Sorry.
It should be t raised to minus 1 by 6.
T raised to minus 1 by 6 whole thing raised to t. It's a product of t things. Right. So now we must have fixed it before, but
How did we work that expression inside probability? And so gamma is related to the minus. That is why this formula.
you mean the first line? What?
Yeah, inside probability expression in first line.
How
How are we writing?
because no, so this is the probability we are interested in. Yeah, that the measure is in the bad case measure could be large. So if the measure is larger than 2 raised to n by 2 minus k, what would it mean? It would mean from our older formula there was this formula, right? So from this formula it would mean that all these di's are small. They are in fact smaller than k by t. Well, the sum is smaller than k, because if the sum was larger than k, then measure will be small. So the sum of the discrepancy being smaller than k, that you have estimated here, this, right? So we just reinterpret that error probability. It's basically the measure being large that that was our original goal anyways. And then we fix k to be t raised to 1/3, we get this probability to be t raised to minus t, and obviously we should fix t to be exponential in n raised to 1 by delta. So think of t as 2 raised to n raised to 1 by delta. So for that larger t, your minus t will be correspondingly small, probability will be small.
So why did we fix the measure to be less than t to the 1 by 3?
Why did we fix k?
I guess it will all work out in the end, right? Probably an optimization.
No. So the thing is, it is already determined. So square root t is what you have as bi. So k has to be smaller than square root t. If it is square root t or exceeds, then the error term is 1. It's useless. I mean, the error probability is 1 then. So you want it to be smaller than square root t. So you can pick anything which you like, smaller than half. And I think I prefer 1 by 3. Yeah, so one technical point is that these constants which we are using, for example, also in omega, big omega, they are absolute constants. They don't depend on anything. They don't depend on delta, they don't depend on k or t or whatever. So these are absolute constants. There is no hidden constants like in some older proofs. Okay, so yeah, so just rewriting this. So probability over y that gamma is greater than s times. Okay, so now we are moving to f, which is low degree monomials plus sum of t s many t products like g, right. So now you will have s times 2 raised to n by 2 minus k, which is s 2 by n 2n by 2 is the max, and you are reducing it by some exponential like epsilon 1 by 3. So probability that the measure of final polynomial f, right, the multilinear depth delta circuit, that measure is larger than this. This is s times so the previous thing times s. Right, so that finishes the proof of the lemma. So in this last statement there are two heavy things hidden in the notation. One is that the measure is large by that much amount, so closer to s times 2 raised to n by 2. This event, the probability is also dependent on s. Okay, so the probability is upper bounded by s times this e raised to minus t kind of a thing. So if s is larger than this e raised to minus t, then this probability estimate is giving you nothing, right. So the size is actually being used in both the places. The measure being large, there s appears, and also in the probability, error probability s appears, which is fine because we will anyways assume s to be small. I mean, we will say that if there is a multilinear depth delta circuit that is small, then this error term will also be, error probability will also be small. So in other words, for usual partitions, for random partitions, the measure will be small, right? So it's in the correct direction, but all this is really dependent on S. Otherwise, it doesn't make sense.
For GIs, it was S3, but
For G, it was correct. Yes,
but in that way F was broken. So G's
correct. Yeah. So there might be many G's. So if you take way too many G's, then you don't get any error probability.
especially that brick was size 3.
Right. Yeah. So that's a technical thing in this estimate, that S is appearing on both sides. But that is consistent with our final goal. Yeah. So if this part was worse, if it was too large, then we would not have been able to use this for any lower bound purposes. So good thing is that on both the sides these S-free parts are comparable, and that is what will also give us the lower bound on S. So right, so thus there exists this absolute constant epsilon such that if S is smaller than exponential in t raised to epsilon, then the probability over y of the measure being 2 raised to n by 2 is less than 10%. Right, this we can deduce from the above. So epsilon equal to 1 by 3 may not work, but you may suitably reduce epsilon below 1/3 to some absolute constant, such that this probability here falls to 1 by 10, and here we are saying that the measure is maximized. So measure being maximized happens with very low probability. So what should your F be now for the lower bound? Do you remember this probability for F equal to determinant? When F was determinant, then I think this probability was quite high. So on the other hand, so which implies that F can compute determinant. How much was it?
It was S times 2 raised to n minus by 16.
No, that cannot be. Anyways, F determinant only if S is greater than t raised to epsilon, exponential into t raised to epsilon. Which is exponential in n raised to omega 1 by delta. So if for determinant we get this size lower bound for multilinear depth delta circuits. Note that you are getting 2 raised to n raised to 1 by delta, So for delta constant, this is an OK bound. It's not optimal, but still you can call it exponential. You may even take delta to be just below log n. Even for depth delta small o of log n, you will get some lower bound. But that will not be exponential. Okay, so depending on how close to log n you get the depth. So basically at delta equal to log n, this will completely break down. And which is a depth that is realistic. To compute determinant, n cross n determinant, you would have to go to log n depth. And at that depth, this proof breaks down. It doesn't give you anything. But below that depth, this gives you something. Okay, so that is the limitation of this technique. So this finishes Raz and Yehudeyov's proof for determinant, n cross n determinant, and the same thing for permanent. Against constant depth multilinear model. Okay, so any question? So we have done it first for multilinear depth 3 and then we generalize that idea to other constant depths, higher constant depths. So do you want to generalize it further? So now we can try to generalize it to formulas, multilinear formulas. Okay, so there the thing is that we are not saying anything about the depth. Depth can be arbitrary, but then it will not be a circuit, it will be a formula, right? So it's a generalization in a slightly different direction. So we can also say something about multilinear formulas. But the bound will be worse. It will not be that kind of exponential lower bound as we got for constant depth formulas, multilinear constant depth formulas. Yes, of course, the T product idea will not work because that calculation we have done, that we cannot make it work for delta close to log n, and in a multilinear formula that could be the depth, could be log n. So a different product is considered. Called log product. So again it is a product of T multilinear and disjoint support or disjoint variable set GIs with partition since it's multilinear, the underlying variable subsets are disjoint, so that induces a partition into x1 to xt. So this will be called a log product. So what do you think is the definition of a log product?
Log data.
No, so remember that whatever you define here, multilinear formula should reduce to this. there should be a structural lemma.
Yeah, but the structural level last time was not clear, so it seems hard to come up with a definition.
Mm-hmm.
I said it was not intuitive that such a structural lemma would exist. So try to come up with a definition while keeping a structural lemma in mind would probably be difficult.
So previously we had said that each of these xi's is at least t. So we certainly have to relax that, and now what we will say is, I mean x1, x2 dot dot xt, the sizes may be gradually reducing. We'll allow the size to gradually fall down, and that will basically be by 1/3. So you start with something and then you start with n by 3 and then you allow reduction by 1/3 factor. So this logarithmic fall.
That's not intuitive, right? And then that formula is reduced to that.
Yeah, so multilinear formula you can reduce by induction to this. So again there will be an inductive proof. Yeah, it is kind of consistent with the log depth. So there the variables, if you start from the bottom, the variables are growing by a constant multiple at each depth. If for all I the size of xi is at least n by 3 to the I and at most 2n by 3 to the I, and eventually xt is 1, only one variable in xt. Okay, n is the size of x, as always. So that's a log product. So now we have to do two things. We have to show that formulas have this structure. They can be written as sum of log products.
So it is called log product because T is log.
Yes, so t is around log of n.
Definition doesn't match with T product definition, right?
Yeah, so as a t product, this is you can only say t equal to 1 because xt is 1. You can't say anything more. Yeah.
Because it's product of log and J.
Yeah, so it's not that the xi's are all large. They start large and then they gradually fall. It's actually pretty precise because you were saying that xi is between n by something and 2n by something, so you have a good idea of how big and small xi is. So this can be achieved. That is first, and second will be studying the gamma, properties of gamma on this product. Which will again be by discrepancy. So any size S multilinear formula phi can be written as a sum of S plus 1 log products. Yes, what is the inductive proof? So x1 size you want n by 3 to 2n by 3. I think in this case we don't need anything except this formula structure.
At the multiplication gate, we can just group up a bunch of inputs so that the total number of variables becomes close to half. Deduct on the rest.
Yes, so you identify, so again from the bottom, when you see the variable subset is going to slowly increase. because you start with variable subset singleton and then you reach n. So as you are going up, it has to keep increasing. So at some point you get a node where the variable subset is between n by 3 and 2n by 3.
So can we not?
It could be too large maybe.
Can
So
we
yeah.
not do it this way? Like the sum that we have, that can just be the, I mean, inducting from the top. That sum of s plus 1 thing that we have, that can just be the addition gate at the top.
Mm-hmm.
And then, so then you take each multiplication gate that will have a number of inputs. Some, it will have unbounded number of inputs, but some of them together will span like between 1/3 and 2/3 the total variables, and then the remaining will span the remaining variables, and we can just induct.
Yeah, so use that identity you get for formulas, f equal to gv whatever. Yeah, you need that identity. That is why you get a sum, because of that identity inductively. So just for sanity, let n be slightly, I mean moderately large, n should be at least 3, otherwise division by 3 will not make sense. And phi computes a polynomial f on the variable subset x, variable set x. Right, this case of n 2 or less you can see as a base case, it's a trivial base case. Otherwise, when n is 3 or large, then we'll induct on the size, I would say, on S. So let V be a node in phi that depends on variable subset xv such that xv is between n by 3 and 2n by 3. So why will this v exist? Well, this xv greater than or equal to n by 3 is clear, because you are going from variables one variable to n variables. So at some point you have to cross n by 3. But why this upper bound to n by 3? So for that, I think you have to assume some, maybe assume Fanon to be 2 and.
Fanon is 3, you could have n by 3, and then all of them will be multiplied in one step and could come n.
Mm-hmm. Yeah, so Fanon less than or equal to 2 will be enough. So you can assume the canonical form. So phi has Fanon. At least I think Fanon Fanon 2 should would be required for this, and it should also be enough. Yeah, so make this deduction, get a node.
Yeah, then it makes sense, because if the degree jump from something below n by 3, the degree can't jump from.
No, but we are not talking about degree.
Or the number of variables cannot jump from something below n by 3 to something above 2n by 3, because
Correct.
there will just be a union.
Yes, right.
And because you need multilinearity also.
That I am not. Okay, yeah. Yeah, that is true. And multilinearity. So it's syntactically multilinear. Every node you have multilinearity. Right. So at some point, at least one of the variable subsets will cross n by 3, and the first time that happens, each of them is n by 3. So the resulting variable subset cannot exceed 2n by 3. That's the full argument.
Formula assumption will help in breaking.
Yeah, so that identity which you always use.
There is a part.
Right, so by the formula, we have this usual identity. F is whatever is computed at V, that is phi V, times I think we call it derivative f v prime plus f v equal to 0. Right, so where phi v is V's output, f v prime is has variable subset x v complement. Sorry, x minus x v, that's it. Yeah, you don't know anything else. So with respect to v, you can decompose this formula for f. So phi v becomes your starting point of log product. Right, this is basically what you have done in the induction step. That phi v is your let's say G1, and G2 to GT you will just get inductively from f v prime. It is now believed that measures don't exist for Vp different from Vnp.
Why?
It's a paper which you should present. I'll tell you after the talk.
It just proves that some measures cannot separate Vp and Vnp, right? Like partial derivative.
No, you read it and then we'll fight. Yeah, that's the structural lemma. So this definition is log product is good enough to be applied to multilinear formulas, but now the next question is how does gamma behave on log products, right? So gamma will actually not give you a stunning lower bound, it will just give you something, and I'll also skip those calculations. You just have to repeat this hypergeometric stuff. So now we estimate gamma yz on a log product h1 dot ht. T is naturally at most log, and the support the variable subset of these HIs is gradually falling from n by 3 to 1. Yeah, so actually can you guess from the big calculation we did last time what this measure will be, is expected to be? So you want to show that this is small, but
2 to the n by 6. Maybe slightly bigger than that, but only in constant. Or,
no, so the problem is that yeah, maybe I should write that down. That is an important thing. So
maybe n by 3.
no, all that is wrong. In the T product case, we got the error probability something like 2 raised to minus t. Right? Very vaguely speaking, you got 2 raised to minus t. T was something like n raised to 1 by delta. Yeah, that's a mistake. I think this is not exp. Right, but t should not be exp, right? T should be just n to the 1 by delta, right? This should be, yeah, That was a mistake. Yeah, so in the t product case, we took t to be n to the 1 by delta, and that is what you then get in the exponent of error probability. So the higher delta is, the worse, a weaker result you are getting. So just from that, actually, you can see that now you will get something, maybe I further change this. It was something like n to the minus t that you got. Now in the log product case, t is not that high. I mean, the things that you are multiplying, they are not so many. So you will get error probability just like n to the minus log n.
This is the error probability, but what is the measure that you expect?
No. So error probability determines now everything. If your error probability is too high, or your result is worse in terms of probability, so then you can only say that S is at least n to the log n. You don't get an exponential result. You just get a quasi Pauli lower bound, right? So previously, by picking t to be, let's say, square root n, you could have gotten n to the minus square root n lower bound. Now it is not possible. So now you will be stuck at n to the log n.
But so this will be the error, right? But what will be the actual estimate from which we deviate with this much probability?
That remains the same, but doesn't help, because you are getting that the error probability is s times this. So if as soon as s exceeds n to the log n, you are saying that your event happens with probability at most 1, which is not saying much. So that is the technical thing in the previous proof, and it kills you here. Okay. So yeah, the way, I mean, some more details here. So around half of log n, I mean, this is coming from log of square root n. So around log of square root n, many of these HIs do depend on greater than equal to root n many variables. Right, this is true. Which of these HIs? The first ones. If you look at the first log root n many HIs, obviously they all depend on around square root n, at least square root n many variables each. Yeah, so on this, now you apply the hypergeometric calculation. So these xi's are big enough, and when you will do a random partitioning, when you will randomly pick y, the discrepancies in one of these would be large. So that part of the calculation is good, but then the probability you get is bad, and you have to pick the worst thing. So you will only get n to the log n. So on doing the probability calculation, we will get that gamma of h1 dot dot ht is high with probability smaller than which multiplied by s. So that becomes your error probability. So as soon as s exceeds n to the log n, you are in trouble. This is then a bad error probability. So what you get is determinant n cross n or permanent n cross n requires n to the log n size multilinear formulas. Right, so this is also a result by Raz. In fact, this he did first. This super polynomial or quasi polynomial lower bound for multilinear formulas. Then it was generalized to constant depth multilinear with Yehudeyov later. So any questions? Right. So as far as I remember, this is still an open question. Improving this lower bound for multilinear formulas. To something like 2 raised to n raised to epsilon for a constant epsilon, something almost exponential instead of quasi polynomial. Well, okay, what is the best formula you know for determinant? What is the size? What is the formula complexity of determinant?
Raj proved, I guess, that.
No. So just because there is a poly-sized circuit for determinant, so circuit has this nice property that you can bring it down to log n depth with multiplicative or product fan in 5, and then you can blow it up and make it a formula. So when you do this blow up, you get an n to the log n sized formula. So determinant has a formula of size n to the log n, but it's non-multilinear, of course, because even the circuit was non-multilinear.
Is this construction a general construction or
Yeah, this is for VP.
for any VP circuit?
Yeah, any circuit of size S, because the results are general. You do depth reduction, bring it to this nice form, and then make it a formula. I mean, making a formula means that wherever you see fan in 2, you make copies. Sorry, fan out. Yeah, wherever you see a fan out of 2. So in the canonical form, fan out is at most 2, just like fan in is at most 2. So wherever you see fan in 2, you make a copy of both these things. So every fan out you are blowing up by S, the size, right? And the depths are, the levels are only log n. So you blow up to S to the log n. That's a general reduction. So hence determinant has a formula of this size. So this n to the log n is not so arbitrary. There is a philosophical reason why it is coming, because actually this kind of non-multilinear formulas do exist, and this technique is getting stuck there even in the case of multilinear assumption. But you would expect that when you have multilinearity assumption, then nothing should exist. It should be just 2 raised to n size, but that is not known. So improve multilinear formula lower bound or upper bound. I mean, both the things are open. Yeah, so I think next topic I should start tomorrow. So from tomorrow we'll move to a different model, depth 4. So till now you have seen two measures. I mean the basic measures were only two, and each of them were in their most beautiful form at the level of depth 3. Right. So we started with this partial derivative, this depth 3 lower bound over finite fields. Depth 3 over finite fields, that gave one measure, and this was multilinear depth 3 that gave another measure. Now we will go to depth 4 and define and work with the measure there. And the model that we will study and prove lower bounds, it's a highly successful model in the last 10 years, maybe even less, last 6-7 years. So this is degree restricted depth 4 circuit. Okay, so this will be sigma product, where we will restrict this A and B to slightly smaller than what it can be. So in the depth reduction you saw that this A and B you can bring down to square root d for a degree d polynomial computable by a size S circuit. So we can bring it down to depth 4, where the size will blow up to S to the square root d, and A and B will both be square root d. So actually we will take A and B to be square root d and prove lower bounds. So that is the degree restricted depth 4 model. I mean it seems to be a weaker model than depth 4 because degree could be as high as the size. Right? There is no reason for it to be square root of the final degree. So at the face of it, it's a restriction, and for this we'll see a measure and then use it to prove strong lower bounds, quite strong lower bounds.
The measure used for this was proved that what you were saying.
Yeah. So